Good morning, children. Today we are going to discuss another paper. Today, the paper we are going to discuss is 2019 summer physics 1 paper. Right, let's go ahead with that paper over here. So this is the paper we are going to discuss today. Right, okay. Let's go ahead. I think one of the term tests you received some questions from this paper as well. So you may be kind of familiar with this. So let's go ahead and see. Right, okay. Then when this referring to the first question, they mention which of the waves is a longitudinal. Longitudinal means we know that when the particles are moving parallel to the wave, propagation direction is called the longitudinal. If I just repeat it back, the particles are vibrating. If the wave goes like this, particles are vibrating parallel to the wave propagation. That is called longitudinal. Transverse means particles vibrate perpendicular to the wave propagation. This is a longitudinal, this is a transverse. So here the best longitudinal wave where we know, yeah, in our day-to-day applications of the sound. So simply you can cross sound as the answer. Right? Draw a straight line linking the electromagnetic wave to correct hazards. Sorry. So you know that the microwaves can be easily, what happened with it? So you can say the best X way of memorizing this is, you know that microwave we use to heat food. Means like it can be easily heat up the any kind of cells or what kind of a substance which contains water. So answer is here. Simply you can write the answer for that, right? Then if you come across with the next one, infrared. IR means definitely we know that IR is having some kind of like, rather than blindness, it won't go for that much of a hard problem with this, like temporary blindness can be come across with ultraviolet, but infrared won't make much of hazards, but it just makes some small skin burns. Yeah. So it can be over here. So cell mutation can come across from where? From gamma, those like waves, gamma, alpha, beta, those can be caused some kind of cell mutation, not the any other thing. Prominently cell mutation come across with gamma. Alpha and beta can be occurs, but the problem is that they cannot much penetrate through your skin, therefore it won't make much impact like gamma. So that's a factor to understand. Which of these uses X-rays? Checking the broken bones, cooking food, detecting forged banknotes, smoke detectors. Checking the bronze, this is simple answers. We know that from our day-to-day application, this is the answer. If you review the other waves, other answers, what are the areas you are using for that? Cooking food, what do you use? You use microwaves. Microwaves you use for cooking foods. Detecting forged banknotes, what you get? You use IR, infrared. Smoke detectors, alpha radiation. Those are the facts those are the waves you'll be using for this kind of purpose, right? Okay, let's go ahead with that. Which of these use of infrared waves? Oh my God, we already discussed this matter. IR. IR we use to detecting forged banknotes. It's pretty simple. Answer we are users. IR. So IR we can use uh, IR you can use for these ones, infrared. Sorry, I just made a mistake over here. This is wrong because detecting force not IR. What do you use? This is UV. We use UV lamp for that. It's like a blue color lamp. So this is way. So which one you use for the infrared? Infrared you can use for several purposes. IR we use in different approaches. First approach is we can use in because you know that IR can heat up the objects. So because like it contains some amount of heat, checking the broken bones, it's not there because already picked with the x-rays. Cooking food may be some kind of a correct answer. Let's go ahead with this much. Detecting fraud, no, it's not. Sterilizing medicals, no, sterilizing we use gamma. So this is ultraviolet, and this is anyway x-rays, but cooking food, this is the most appropriate answer for this. But basically we use cooking foods for what? Use microwaves of that, but IR also can be used because it's a heat substance, radiation. So therefore, we can use that one as well. So it's not a much problem with that. The question is about magnetic field. Describe experiment investigate a magnetic field pattern around a permanent bar magnet. You may use a diagram to for help you, right? Okay. Yes. So already, so the basic experiment, we can use two experiments. First experiment is ion filling. What you can do is you can keep just like a piece of paper, just like this, and we keep our bar magnet underneath of this. We just learned this experiment before. We keep this bar magnet underneath of this one. So they're not should be gap. I just draw it just to understand this one. So this is the North Pole and this is South Pole. Then what you need to do is we just put some iron filling on that. We just put iron filling so onto that, and we just tap on this one. So therefore you can see this kind of a behavior around it. So you can see ion fillings are organized in a way of like this. That's an experiment where we can write it. So how to write it? I think we already wrote the answer for this question when you are doing our theory. This is a way of just if I read it out. The first method is take a piece of paper, some kind of a little bit of a cardboard, and put a bar magnet where you need to understand about the magnetic field underneath of this paper, and put some iron filling and slowly tap on this piece of paper. So in that case, you can understand that these iron fillings would be organized in a way of according to the magnetic field. But here you can, from this experiment, you can identify the shape of the magnetic field, but not the direction. If you want to go ahead a little bit ahead with the direction, what you need to do is we just set up this experiment in this way. Same setup with the bar magnet, just like this. North and south. Then we just put you can see, you just put a compass over here. Put a compass, and then you can say the compass will be organized in a way of like this. Then you just mark the dots from the tail of this arrow and the tip of this arrow. Then you can put again, you take it out and keep it again in a way, the tail of the second diagram align with the first dot over here. Then like this, you can put this way. So you can say it's like this. It will organize in a way, just put it here, then just like this. It comes like this way around, it goes like this, and it comes like this way around. Therefore, just like for this side, even you can see the, same behavior if you put it here, not this one. Then here it's just like this, like this, like this, like this, and it comes like this way around. So it just like after you are what you call joining these dots, you can understand the shape of the magnetic field. That is a simple experiment where we can do. But from the first one, you can identify the direction, shape. But from the second one, you can identify the direction as well. That is the advantage of using a compass instead of iron powder, right? The diagram shows a bar magnet complete the shape, so you can understand that these ones are repelling these things, because like poles of a magnet get repelling to each other, and magnetic field lines coming from North Pole and travels up to South Pole. So initially you can see this is a repulsion. Therefore you can just mark like this. You can draw just like this way around, and somewhere like this, and it comes like this way around. That's a way of doing this. Right. The question is about food preservation. The diagram shows how gamma radiation used to irradiate fruit stored in a wooden box. Wooden box, gamma also is This much. Explain why gamma radiation is used instead of alpha radiation to kill bacteria. So you can say that the gamma radiation can travel to much distance compared to the alpha radiation. Yeah. So you can say, therefore, they can easily go inside the fruit, inside the box and the fruit, and it can be kill bacteria. So you can say gamma radiation contains more penetration than alpha radiation. Alpha radiation. Therefore, gamma radiation can go through the box and fruit and kill bacteria. That's the answer for that. That's a simple definition. It's a simple explanation for this question, right? Okay. Then they mention fruit box has this label. These fruits have been irradiated. Explain why food irradiated with gamma radiation is safe to eat. So in this case, you can say they don't have, because if it is irradiated, there's no bacteria in it. Yes, and fruit has, yes. Okay, so these are the two facts. You have two facts for this one. First one is, now it's not infected. So you can say no bacteria present. No bacteria present after the process. And the next one is, but then now during this process, you can see this nuclear substance is not contact with the fruit box. Therefore, there is no, it has a very low chance of getting what do you call that, radioactive present in the fruit. So you can say fruit has not been, so you can say fruit has not been made radioactive. The reason is that for this one, the gamma source where we use with a very short lifetime. As a result, you cannot see any kind of radioactive substance present in the fruit, because one thing is fruit is not contacted with the radioactive substance. So there is no touch with that. And second one is we are using radioactive substances which is having a very short lifetime. Therefore, you don't have much of a problem with that. That's a fact we have to understand. Then they mention a car driver sees a hazard on the road. Remember the fourth question. The graph shows a velocity of a car from when the car sees the hazard, right? Use a graph to determine the reaction time for the driver. So you can say till you apply brakes, it moves at the same speed. So this is the time where it come up with the reaction time. After that only he apply brakes and it come up with this. So you can say it's roughly, you can say 0.95 seconds, right? Calculate the stopping distance of the car. Stopping distance means the speed of it. We know that in velocity time graph, distance measured from which fact? Distance measured from the area of the shape. So you can say it's area half base. Base is 9.5 to 4. So 4 minus 0.95. Sorry, 0.95, not 9.5. From here to here. Into height. Height is 15. From here you can get this answer for that. So you just do the calculation and you can obtain this answer, right? Calculate the acceleration of the car when the car, acceleration of the car when the car is braking means actually this is not the acceleration, this is a deceleration they are referring to. In velocity time graph, how to calculate the deceleration? We need to find the gradient of this. How to find the gradient? Here the coordinate is how much? If I just get the point here, that is x coordinate is 0.95 and y coordinate is 15. Here, if I use this one, x coordinate is 4 and y coordinate is 0. There with that, you can get the gradient by gradient. So you can say acceleration is equal to gradient, that is y2 minus y1 divided by x2 minus x1. No need of writing this. I just wrote it to understand the answer. So you can say 15 minus 0 divided by 0.95 minus 4. Right. With that, you can obtain the answer. So I think 0.95, this is 0.95. I think it's not much clear for you to do it. 95, there with that you can say 15 divided by 8.05. With that you can find the acceleration. Right. Okay. It's not 9, it's 4. Sorry, I made a mistake, it's 4. Just like it's 9, it's 4. So this is turned up to 3.05. Roughly we can get like 3, doesn't make a difference, right? Okay. Did they mention the speed of the car affects the thinking distance and braking distance? Discuss the other factors that can be thinking distance and the braking distance of the car. Thinking distance, if you take thinking distance, what are the facts to be done? So you can say the mental condition. Mental condition can be considered for the thinking distance. What are the other facts? Other facts would be these. If this is bad, you can say, well, if this is bad, thinking distance increases. That's a fact. You write it in words. I just explaining the question. You can write your own answers. Other one is if you're alcoholic. If it is alcoholic, what happened to them? So if it is alcoholic, definitely thinking distance would be high because the reaction time increases. So thinking distance become high because the reaction time is increases if it is alcoholic. Braking distance. What is the condition? You can say tire condition. Tire conditions. What else? Road conditions. Okay, so those are the facts to be written under the this much. The braking system used in the vehicle. Those are the facts, because if you use it right, rather than the drum braking, if you use what do you call electronic braking system, ABS, what do you call the braking distance become kind of shorter. The question is about stretching a spring. The graph shows how the extension of a spring varies with force applied to the spring. The line on the graph shows the spring has been extended to the past the elastic limit. The line has a straight section of the curve section. So what is this region? So you can say this is a proportional region, and after that it come up with elastic region, and it follows up the elastic region and reach up to the plastic region. What is the definition of the proportional region? Proportional region is a region where the force is proportional to the extension. Elastic region means like during the elastic region, if you remove the force, it will reach back to the initial length. Just like rubber band, if you stretch it and if you release it, it comes to the initial length. But if you overstretch it, and if you release it, what happens? But it never reaches to the initial length, comes with the permanent deformation. Draw a cross on the line so that the elastic limit of the spring. So you can put it somewhere over here. It's more, a little bit more than the proportional region. Sketch another line to show that the extension to the change when the force is decreased from a maximum value to 0. Sketch another line to show that how extension will change when the force is decreased from its maximum value back to this 0. So let's see. Yes, Pate, right. How the extension. Okay, sorry, children, there was a small network here again, so it's not working. Sketch another line to show how the extension will change when the force is decreased from maximum value. Where's the maximum value is? Maximum value is over here, Pate. Right, over here is a maximum value. Then from here to 0. So when you remove it, you can say it has already passed the elastic region. So therefore, it come back with a permanent deformation. So you can just draw a line like this, and this is come up with permanent deformation. That's what you need to understand from this one. State with the energy stored in the spring increases when it's stretched, assuming that the spring does not reach the uh, elastic limit. So in this case, if you stretch it, the amount of energy stored in this one is, you can say, elastic potential energy. Elastic potential energy. Sorry. Energy. Elastic potential energy. Right. How is the energy transferred to the spring? So you can say, so how do you give an elastic potential? Because to stretch it, we have to mechanically, we have to stretch it. So therefore, the mechanical energy is the one which is converted to the elastic potential energy during a stretch, right? A student investigate how the current varies with voltage in a filament lamp. Draw a diagram to the circuit to student to use this investigation. So you can say, investigate how the current varies with voltage. There should be a cell, sorry, there should be a bulb you need to measure. So you need to measure the current over here. To measure the current, you have to put an ammeter series to this, right? Then we can put some kind of like some kind of a cell over here to give the voltage. And now the next objective is, what we need to do is, we can put a switch. Sorry, we can put a switch over here to control the circuit in a case of emergency to shut down, and we need to measure the voltage with it. To measure the voltage, we need to make it. Now there is one part is missing. We need to identify, we need to change. The current should be varying. So you can see none of the facts are, it's varying over here because all of this bulb has a like one constant resistance. To control the resistance, what we, so to control the current and the voltage, we put a variable resistor over here. We have to put a variable resistor over here. So from the variable resistor, we change it. With that, we can give different voltages and different currents to the bulb, and we can measure it. Describe the method the student should use for this investigation. What they do is, initially, we set up like this. Set up the circuit as shown. After that, what do you need to do? After that, we need to give different voltages and different currents with it. So what you can get here is that we can change the voltage. Change the value of variable resistor. When you change the variable resistor value, what happens with it? Then when the total resistance of the circuit varies, with that current varies, current and the voltage varies. So you can say, according to that, measure the changing voltage and current. That's a factor we have to understand when you're working out with this question today. Right. Okay. Right. Then let's go to the next part of this question. They mention the student extend the investigator the recording additional data of the lamp. Yeah, he will use method for each voltage. Switch the current on for 45 seconds. Record the current in color. Record the current and color of the lamp. Calculate the power and the energy transferred by the lamp. The student use the table to results. State the units of current. What is the current measured in what? Amperes. Amperes. Right. Then calculate the missing value for the energy for voltage 4 volt. Voltage is 4 and current is 0.9. Power is this part. Then we have to find the energy. Energy, how do you find it? Energy. We know that here this is operated for 45 seconds. Operated for 45 seconds. So you can multiply 45 by 3.6. Multiply 45 because 45 seconds, the power is 36 because we know that energy is equals to, energy is equals to power. What is the energy formula? Energy is equals to power into time. Therefore, we can write power is 0.36. Sorry, 3.6. I just made a mistake. It's 3.6, multiply 3.6 by the time, by 45. With that, you can obtain the answer over here. That's a way of getting it. The color of a star is related to the surface temperature. The sun is yellow. Use the student's result to identify color for a star which is cooler than the sun. Right. So in this case, which is cooler than the sun, that means which is having a low power with that. So which is having a low power than that. So which is cooler, they ask about cooler than sun. Sun is yellow, therefore something which is but which is dissipating a less amount of energy. So it's just like any of these you can be written to red or orange, you can write, because you know that if it is cooler than sun means amount of energy releases is less than the sun. So you can say red or yellow, red or sorry, I think red or orange. It's turn up to red or oranges. Orange. That's what you need to work out with that. I think, yeah.